All right, so I guess we're about ready here to start. So just to let you guys know, if it wasn't for sponsors, we couldn't run these rooms and give you this great event for the price that we asked for. So basically, I want you to know that ActiveState is the one sponsoring this room. If you look on your chairs, you may have seen these little flyers. Do check it out. Again, we're a community event. We do encourage, community sponsorship, and ActiveState is one of those companies that is sponsoring this. They're basically, I'm going to read this little statement from them. So ActiveState empowers innovation from code to cloud smarter, safer, and faster. Built with and on top of various open source packages, including Cloud Foundry and Docker, Stackato is ActiveState's groundbreaking application platform for creating private platform as a service. For more information, see activestate.com or visit them at booth 83 down in the Expo Hall. Now, again, as I said, it's like we're a community event, so do go check them out, see what they have to offer. A lot of interesting stuff happening in the Docker space. And now I give you Matt Porter.
All right, thank you. Thank you, Monty. Thanks. So it's my first SCaLE. I've never been here before. I've had a number of friends and have been here before and told me it was a great conference, and now I agree, now that I've seen it. And thanks to Tom King for inviting me out. So I call my talk Contemporary Device Tree. If you're familiar with at least the concept of device tree, there's a number of great talks about internals and so forth at some other conferences, and I felt that one of the things that was missing is really looking at contemporary, meaning here and now in the present, looking at how it is now and how you can really make use of it. But I also feel very strongly, and I know some friends do too, that you need to understand the history of things before you understand how we got to where we are. So there's a lot of misconceptions about the history of device tree and why we have it in the kernel, so we'll kind of start there. But first, a little overview. We'll talk history of device tree. We'll talk how the Linux kernel uses device tree, some basics. We'll go into some examples, and then we'll talk about modifying it, because the whole purpose of it is you need to modify it for your platform and enable something new or disable something. And then we'll talk about a new feature that came in a 3.19 kernel, which is the dynamic device tree overlays. So a little bit of history. Yeah. So a lot of people these days that are, maybe doing embedded stuff, especially is where this shows up. They always hear about ARM device tree. Okay, it was invented or something around ARM, and that's simply not the case. So if you're an old guy like me or old lady, then you go back to Sun Microsystems, Spark Systems, and it was 1988 that they had open boot, open firmware. It was using Spark Systems, so if you, like me in university, used Spark SLC, very low-end junky systems and so forth, then you probably saw open boot or open firmware on the system, and device tree was used in that. And the device tree would describe the hardware. This became an IEEE spec in 1994. That documents all of device tree at the time, which is a lot simpler times then. And what's interesting is that IEEE spec, it's actually never got renewed, so it's no longer a formalized specification. I think like 98 or something like that. And then where we start running, where a lot of people saw open firmware and device tree was in the Apple system. So all the Power Macs, starting with the first Power Mac, the 7200, 95, used device tree. And then if you recall the history of Apple clones, the Apple clone systems were chirp-based, right? This Common Hardware Reference Platform, and it also specified DT. So you'll find, if you go in the kernel and look at PowerPC stuff, you'll find still chirp support, device tree, and so forth, these systems, like the Motorola Star Macs that killed off the clones. But that's another story for later. And then there's a specification that the IBM Power group came out with, the EPAPR, specified a lot of modern peripherals with DT, and that brings us up to 2008. So, now that we know that it's been around forever, how do we use it in the kernel these days? Well, first we've got the historical platforms. We've had SPARC Linux for years. I used to run it on my SPARC systems, and so they had to pass a device tree in and configure, they would figure out how many CPU cores and so forth from that. Again, all those systems that we've supported in the kernel, right? Power Macs were a huge deal, and so there's been support there for years. What happened was, very interestingly, in 2005, there was an Arch PPC and an Arch Power PC, okay? And, sorry, Arch PPC 64. So the 64-bit and the 32-bit were split. So a lot of us that worked on embedded platforms were in the 32-bit side, and there was a big merge into Arch PowerPC, which if you look in the kernel today, that's all we have left. Part of the entrance requirements of coming in an Arch PowerPC that were driven by the 64-bit big iron guys were that all the platforms need to use device tree. And one of the things that happened in that is there was a lot of cleanup of code, a lot of consolidation of the code in the kernel. Yeah, there was some pain in there. Don't get me wrong. And so, but the end result was this general feeling that the sharing of code got better. There wasn't so much duplication and so forth, and a lot of that was driven by this data abstraction of device tree. And then a little funny thing, and I love to remind people this because a lot of people don't realize that x86 does device tree too. So you can go look and find that CE4100 Falcon files. You'll find there's a DTS file down in Arch x86. So yes, x86 uses DT too, if you find the right platform. I don't think a lot of people like to admit that. So then let's get to the present. Linus made this big ultimatum to the ARM community, 2011. You can go look at it there, and basically said, you know, I'm going to quit doing pull requests from the ARM platform maintainers because there was so much churn in the code. There was so much duplicated code that, like, everything was just happening in the OMAP tree and the MSM Qualcomm trees and so forth. And he got very upset that everybody was blocking into other people's code. There's lots of conflicts on the pull requests that were going directly to him. So after the ARM community talked about it quite a bit, there was a number of people that had been using device tree in the PowerPC community that had been migrating over to working on ARM platforms. Grant Likely's one in particular that drove this, and they felt that the best way to kind of move that consolidation like happened on PowerPC was to mandate device tree, right, for booting on ARM. Shortly thereafter, I mean, it was within 6 months, Ralph decided that MIPS was going to move that way as well. Also, back in 2008, Microblaze started using that, and it was really driven by the fact that FPGAs are very configurable, and it was a natural way to pass in that description. That was the same thing with it was driven to, Grant Likely had worked on the Xilinx PowerPC 405. The hardcore FPGA systems had a similar issue, so you can kind of see that all come together. So enough of history. What is device tree? We really got to understand what it is. It's data driven, right? This is instead of being driven on code for defining your hardware and a platform, now it's a data driven model. Pretty fundamental computer science concept, right? So the EPAPR defines DT very neatly now. Device tree describes system hardware. This is key. It describes hardware, only hardware, not policy, not how you intend to use it, just the hardware itself. Right? And it's a tree data structure with nodes, describes physical devices, and the other key is it describes the device information in a system that cannot be dynamically detected by a client. So what you'll hear a lot in the community is non-discoverable buses, right? And that's the type of thing. It's the I2C and the SPI. It's not, PCI and USB. Well, those are discoverable, right? You enumerate those buses for the most part, and you don't have to have these same features. So for things that aren't discoverable, you can describe them all in this tree-like structure. All right, so basics of what we have in a device tree. Well, we have nodes. Those are just, inside a node you have groupings of properties and child nodes then. So again, tree structure. A property is just a key value pair, all right? And there's several types. So you have text strings. That's just an example, right? Nice, common my string, right? And then you can have cells that are 32-bit unsigned integers. And so this is an example of just 3 cells, integers. You can represent them in any common notation. And then you can do binary data, like we see here in brackets. And then you can also mix those up in a property. So you see like a string and then an integer value and then a binary value and then another string. And then the next key thing in a device tree is the concept of a p-handle. And a p-handle is simply a reference to another node. So we've got nodes, we've got child nodes, we can have a reference over to another node, right? So we have all our basic constructs, and then we've got those key value pairs. And with that, we can describe any kind of hardware. So let's look at device tree source format. If we take this very abstract example, which is, these are not always the easiest to follow, but it at least gives you that syntax. Yeah, I should have a laser pointer, but I like standing up here anyway. So what you'll see is you'll see this node, and so node 1, and then there's a unit address, and that's supposed to be a unique number, typically within a bus or something. And I'll show a concrete example of how a unit address is used in a real physical bus, because it's more meaningful there. What you can see is all these examples of properties being set just like I showed the different styles. And then you can see a child node within here if you need to show a hierarchy of something beneath that node. And so, again, more properties. And then what's interesting here is you'll see a p-handle, and so this is a property that's referring to this node 2 down here, all right? And then finally, a node, you can have a label that's just a handy way to reference it, typically something that's human readable, or maybe it's something that labels it in a sense of how you use it in your particular board implementation or system. All right, so let's look at a real node, and so things start making sense. So what you see here, I promised you I'd tell you about the unit address, and so in this case, this is an OMAP. Well, this is actually, we'll go back a little bit. This is a UART node from the SoC, the system on a chip, that's used in the BeagleBone Black. All right, it's AM335X. And so within the device tree source file, you'll see a UART0 label, so that's a handy label, and then the node name is serial, and then that unit address corresponds to the memory mapped I/O address, right, in the system. And then you have a compatible string, so this is something new we're introducing. This is part of what we'll talk about as a device tree binding. And there's a device tree binding that says if you're describing a UART on an OMAP type system and the AM335X shares the same intellectual property or IP block, all right, as the OMAP3s, then it's a TI OMAP3 UART, all right. And we'll talk about where these things are documented. And then there's vendor-specific properties. This is specific to the TI OMAP IP blocks. They have to have this hardware mod, so that's kind of specific, but it's defined in the binding. And then you'll see there's clock frequency, something that you can't discover, right? The functional clock coming into that IP block is 48 megahertz. So it's defined there using the key value pair. And then there's a register base address, and then the length of that memory mapped I/O region for that UART. Interrupt number, that's our well-known Linux interrupt number. And then there's always a status in a node for a peripheral. The default on these in the SOC file is disabled. We'll talk a little bit more about that in coming slides. And then the UART is capable of being DMA driven, and so there's DMA engine properties here that tell how these are P handles to an actual DMA engine node, right? So we talked about the P handles, so there's an example of referencing another peripheral, and then these are the transmit and receive DMA channels. So that sufficiently describes that UART hardware and everything you need to use it. And you can see what you'll see in every one of these slides. You'll see I reference in the kernel. You can go look at the mainline kernel and look at that file, and you'll see this in the full context. Okay, so how does a driver make use of device tree? Well, the first thing is in the kernel, you have to bind a device to a driver, and once you do, it will probe the driver, and that's the entry point to start initializing it. So how do you make that happen with device tree? Well, in your device driver, you'll see very nicely, and I've highlighted for you that this OMAP serial driver has a table, right? OMAP serial OF match, and you'll see it's compatible with a number of different types of these UARTs. So each is a separate compatible string, and then what happens here is you register your OF match table there that has all your compatible types. And once this driver registers, when it matches at boot time with the OMAP3 UART that you define in the device tree, then it will probe the driver and your initialization starts. Okay. So as an example of a driver type node and so forth, and then there's the concept of a platform example. And so if I need to enable, right, I have that UART node, but as I showed, it was disabled, right? Let's say that I want to enable that node on a particular platform, in this case of BeagleBone Black. Then what you'll see in this AM335X Bone Common, there's a couple things going on. In a modern SoC, you have a lot of pins or pin mucks because the packages are so small, and so there might be 8 functions or so typically. So right here, we have all the pin muck settings are described for the UART. In this case, it doesn't have any flow control necessary on the debug port, so they're just defining the offset to it, and it's input pull up. You can set in the pin mucks as input output. It's very specific to this particular SoC what these settings are, and then what happens is in this file, it actually overlays some settings on top of that previous node I showed you that came out of AM33XX DTSI. There are these settings overlaid where we say, okay, use pin control, which is a subsystem in the kernel or a binding to one, UART 0 pins, right? So that will bring this information that on this platform, we want to pin mux things this way, all right? So that references this node up here, and then the really important thing is marking that node OK. And what that does is it will actually, at boot time, it will instantiate a Linux device, okay, in the Linux kernel driver model. And that will make that active, and that will allow it to bind with that OMAP serial driver. And until you do that, as long as that node's disabled in the default AM33XX DTSI, it won't even show up in the system. So that's the key to that, and that's the default DTSI file in the kernel. The UART0 is the debug UART found on the BeagleBone Black. So that shows you how that gets enabled. On another reply, the reason they disable it, the reason they disable it is it just depends on the platform. In the base file, they typically disable everything, and then you let the platform or the board-specific files enable what devices you actually bring out. So again, we go back to EPAPR. We want to understand better what these device tree bindings are, because they're really the key to everything.
Just real quick, so what's the order if there's multiple files that talk about the same node? What's the order that those changes or those things are applied?
It's all based on includes, and I've got a slide that tries to visually show that. I'm really bad at drawing stuff, but I tried my best. I'll show you one of that. We'll come back and see if that answers it for you.
Would the same concept go on with the U-boot bootloader? Would you use the same DTS file for both kernel and U-boot?
You can, but it's not quite there today. Boy, I wished my colleague Tom Reaney was here. He's a U-boot maintainer. So there's some work on going to use the same device tree blobs, and I'll get into what a blob is here in a moment, to feed U-boot as well. It's a little bit trickier because you're so early in initialization, right? But there are some platforms using modified DTBs. If you look at the NVIDIA Tegra stuff, Stephen Warren's done a lot of work to actually drive all of their U-boot off of it's not the same DTS as the kernel uses though. But so it kind of defeats purpose, but it's at least a move towards that. So yeah, there is some work and interest in that way, or in that direction. Especially if you're doing a lot of things like, recovery type things and a lot of work in your bootloader, it starts to get more important where you want to just, multiple versions of systems and just deploy a different DTB would be very useful there. Good question. All right, so EPAPR, a binding is how specific types and classes of devices are represented. All right, so the bindings talk about standard properties like that compatible string. That's a generic thing that you'll find in every binding. All right, the reg property that I showed you with the memory mapped IO address, that's a defined base thing. You actually find that in EPAPR. And then when you get into specific things like the DMA properties, those are like a binding just for a class of DMA type engines, right? So these are maintained in the Linux kernel these days. You'll find them all down in documentation, device tree bindings, and then the group maintaining that follow all the standards set down in the original IEEE 1275 and EPAPR. So again, there's a lot of basic concepts, some naming conventions, that if you want to understand this more deeply, you go read 1275 and EPAPR, and then it's easier to go and look at the bindings and understand the base properties that are used in all of them. So each type and class of device that we deal with in the kernel or on any system have a DT binding, and it'll tell you what the required and what the optional properties are, and any time that you list one out in a device tree source file. All right. I just left this in because I picked the worst example. It was a great example of how if you ever do kernel work, it's always hard finding a good example. So I picked the simple one because I love my BeagleBone Black as the example platform, and this binding that you'll find here, I show where you find it here in OMAP serial.txt. It doesn't have all the properties that it needs, actually. This is a pretty old one, and I think it's just bit rotted, and nobody has brought this up to speed. So that's where I'm saying this is a bad example. It's missing the DMA properties that are actually used in the DTS file. So it's wrong. So I'll fix it for you. This is how a device tree binding looks for this particular thing, if it has, and I have to send a patch for this now. if it has all the properties that we saw in the previous slide that they're actually using in the DTS file. So you have to say, well, the reg property is required. If you go look at other bindings, IMX28, IMX6 stuff, you'll find that they have the reg property, right? Interrupts. On the previous slide, you'll see that it didn't have reg or interrupts, and it didn't mention DMAs. So I added those in. And typically what a binding looks like is it will also have an example of use. So I showed, that's just a fragment of it. Obviously, it's longer. So that's where you go and see how that class thing should be implemented in your DTS file.
Quick question about the DMA. So assigning a DMA channel, is that really the fixed ones inside the chip that are, or could they have been assigned dynamically, only they're making it a standard to use these channels with?
It depends on the platform. A lot of these OMAT platforms, they're fixed channels. So you go to the TRM and it's got a list of all the channels, as you know, on TI-81XX. There is actually, along your question there are some that you can dynamically assign if they're on like the crossbar, and there's actually special properties in the same EDMA DMA engine driver has a special thing so you can set that crossbar and point at different places. So there's part-specific properties as well, all right? But you don't, that's actually in a separate node. So if you were going to route a DMA channel on the EDMA, there's actually, when we reference with the P handle, right, the AND EDMA, we go over to the EDMA, you can actually overlay, put a crossbar property in, and tell it to steer one of those one of those DMA channels to a specific open one on that. So I hope that answers it sufficiently. All right, so that's your example of a proper looking binding. Most of them are well documented like this. I just thought it was funny that the one I picked was bit rotted. So how do we manage device tree source? What do we do with this, right? We looked at all the syntax. We haven't talked about what you do with it yet. We just talked about describing stuff abstractly. So the way we use it, whatever architecture we're on, you're going to find them in ArchFoo, boot, DTS, whatever your architecture is. You'll find all the DTS files for everything that's supported in the kernel. So ARM, obviously with that being such a big push and so many platforms, you'll find just a ton of them. It's almost overwhelming looking at how many is in there. But all these other architectures have them in the same place. So that DTS file gets compiled into a device tree blob, all right, DTB, and all that is a binary representation of that. That DTB is then passed to the kernel at boot time, all right, and then all the devices, I was saying how when we mark things status OK, it will instantiate devices for each one of those things that we've marked OK, right? Those are active nodes. And then, going back to the gentleman here, had the question about how the ordering of things. So DTS files may include other files. So it looks just like our friend C code in that sense, or any other thing. So here's the thing I promised with my excellent artistry skills. So again, why I picked on this platform is it actually is kind of represents well this type of inclusion tree. So we saw earlier that UART node was down in this DTSI. Most platforms will describe the system on a chip in something like this, in a DTSI. That's a DTS include file. And then in this platform, there's two variants. There was the original BeagleBone, it's now BeagleBone white. And then there's a BeagleBone black, and they have some peripheral differences that require a different description. So this same SOC file, it gets included by this EVM DTS. There's a expensive evaluation board from TI, and it just needs to directly include that. Some things that were common to both of these variants of BeagleBone Black are in another include file, right? And this includes this file, and then each of these include the common file, okay? And so that's how the orderings figured out. So it starts based on the topmost include file, the preprocessor and processing that DTC does.
Yes, they always name the top level.
Yes, that's the convention. There's been some vendor trees where they depart from that convention, but yes, and if you're looking at a proper mainline Linux kernel source, then you'll see the convention is always that top level board, as Stephanie is saying, is the DTS. Right? So you can always start there and drill down through at whatever platform you're looking at. So how do we compile DTBs? With a device tree compiler, of course. So DTC is used. There's an in-kernel copy of DTC that's used as part of the build process. It's in scripts DTC. They do an import from the upstream, which is also managed on kernel.org occasionally. If you're doing, let's just pick on ARM since I'm using an ARM example. This works for anybody, but there's a make DTBs target, and down in your Archfoo boot DTS, that make file has a list of everything, all right, that's in there, and so it will build all of them, okay? Also, the in-kernel DTC runs the C preprocessor, which is nice because I think that came in a year ago, 9 months, something like that. The raw DTC compiler does not use a C preprocessor, and one of the problems is that you get into a lot of like pinmuck stuff where you've got bit fields and so forth, and obviously having the C preprocessor allows you to put some human readable names into these DTS files. So it's really nice. A lot of the stuff's cleaned up in the kernel, and hopefully you'll actually see readable DTS files, because it's really hard to read that stuff without all the pound defines on those things. Let's see. So if you want to invoke DTC directly, it's not any big surprise. You tell it input of DTS type or output DTB type. It has some other options. You can look at those, and output files .dtb, inputs a .dts. And the DTS is what we saw. That top level file is what you'd handle it, and it would go through and work through that list. All right. So let's get to the fun part, because we talk about all this stuff, but what we really want to do is like modify a DTS file. How do I actually add a device? And the common thing is somebody's got one of these community boards. It could be your Raspberry Pi. It could be, a Miniboard Max. It could be a BeagleBone or whatever you have. You've got some whiz-bang cool I2C device. In this case, we do I show a boring one, an AT24 compatible I2C serial EEPROM, okay? And you want to wire that up, and you want to make that work in Linux, right? The first thing, I show this example on a BeagleBone Black. So this is a real working example. The first thing that I would do in a conventional DTS approach is I need to go modify the DTS files in the kernel, because I need to get the I2C controller turned on that I've attached to, because nobody's using it in the default case. It's not hooked to anything on the board, so it's off, right? And somehow I need to tell the kernel that there's an I2C device, because you can't probe for I2C devices. Somebody will say you can, but it's destructive and dangerous. That's why we don't do it. So what you would do is, in this file, and unfortunately slides are the worst way to show code-like things. I have these fragments. If you go into this file, you need to, and I kind of showed some highlights of this in the UART example. You're going to need the pinmux, okay? Maybe on your platform it's already defaulting to that, but it's best to go understand the pinmuxing on your SoC. So I have to set this thing. So these I even specifically say P9. There's a P9 header. Pins 17 and 18 have this I2C1 bus. It's the second of 3 buses on AM33XX. And the I2C data and clock signals are available on that if we mux them into mode 2, okay? So we add in this node here into the PinMux. There's a PinMux node, and there's some other things in that node that I can't show context-wise. That's why you'll see my little dots there. And then what happens is we need to modify the I2C1 device node. So as I showed earlier, like the UART node, it's off by default. It's the same thing with the I2C nodes. You can go look down in the AM33XX, and it's off. So what we do is, in our top-level DTS, where we're interfacing this I2C device for our board, we're modifying that DTS, right? And we go and we say, okay, I need to use these I2C1 pins I'm defining, okay? And I want to run at 400 kilohertz, right? You run typically 100 or 400 kilohertz, or you could run higher on some I2C controllers. In this case, our serial EEPROM can run at 400 kilohertz, so we tell it that's the clock frequency we want the controller to run at, and then we turn the controller on. Status OK. Now, the next interesting thing when you're adding an I2C device is I2C devices are shown as child nodes. We talked about child nodes. That's why we have child nodes in this tree hierarchy, is we need to show that any I2C devices that we're adding onto this board, we need to represent them as a child node within that I2C controller we just enabled. So what you'll see here is, right, our AT24 at 50. Now, this is another good example of how a unit address is used. Typically these EEPROMs, the default address will be hex 50. So that's what you see used for the unit address. So that has a unique unit address. And then in the binding for the AT24, which it just happened to be the Atmel part that started off this whole thing. There's a lot of compatible parts. It defines this compatible string, and you can pass in AT and then whatever. There's a number of different sizes. In this case, I chose 24C256. There's properties that are specific to this binding, like the page size. That's helpful to tell the driver what the page size of the device, because they can't discover necessarily the page size. And then in this case, our reg property means something different, because it's all contextual. Okay. In the previous UART example, our reg property was defined as the memory mapped I/O address and a length. In the context of an I2C client device, or device on the bus, it's the actual I2C address. And the binding explains this. So if we were to go, I don't have a slide showing that particular binding, probably should have, you'll see that it says reg, this is the I2C address of the device, okay? All right, and so when we turn that on, it will instantiate a device for the I2C controller, but not only that, it will also instantiate an I2C device. In the kernel, the struct I2C devices actually instantiate a new device on that bus of the type AT24 with those properties.
It doesn't matter what you pick as your unit address, as long as it's unique.
Yeah, technically you can get away with having that, but it would violate the binding, right? But yeah, that actually you can get away with typoing that. All right. Okay, so that shows the I2C example. So now it's time to bring in how we can do this even easier. So dynamic device trees are a concept. Everything up till now, everybody has always compiled the device tree from source. It's a static blob, and you pass in the kernel, and it never changes, ever, until you reboot and load a different one in. So I say that, but Power architecture, the high-end big iron PPC64 stuff from the old days, they actually had a concept of a live device tree. It didn't work very well. They actually can only make destructive changes to live device tree. It didn't preserve things and so forth, so it wasn't actually useful. one of the problems is you think about this example I just gave on a BeagleBone or on your Raspberry Pi. It's kind of inconvenient to have to compile and reboot when you're wiring something up because you can just hook them up, right? So a lot of us noticed that on BeagleBones with the pluggable capes and so forth. So a colleague did Cape Bus in 2012, and that had the early version of dynamic device trees where you could plug a cape in, it would detect on an EEPROM, and it would actually modify the device tree live, and it fixed a lot of the issues that the original Config OF Dynamic had. Like I say, it was driven by, the need for that was driven by looking at these pluggable capes, and we couldn't detect everything. And that actually shipped, if anybody's used the 3.8 kernel stuff that shipped for a while on the BeagleBone original and the BeagleBone Black, then you probably ran into the Cape Bus and DT fragments. That approach was wrong. It's not, shouldn't be a bus, and part of those discussions led to changing how this would work upstream and introducing modern dynamic DT overlays. So those went in 3.19. There were some previous pieces that went in 3.17 that were infrastructural to make this happen. But what happened was it introduced into the kernel concept of the DT fragment, and that's just a device tree blob that contains symbols that can only be resolved at runtime. So it's a runtime linker for these fragments, okay, in the kernel. So if you can imagine our example of those I2C pieces, in theory, if you compile that right and tell which things point outside to the base DTB, you can theoretically go and resolve those and insert it into the running kernel and get those devices instantiated. So that works in practice now. So you can insert a DT fragment into the live tree at runtime now, and you can activate it. So the inserted fragment becomes part of that tree. Once it's in, if you cat the new sys device tree file, you can actually see that as part of it. It looks like it was just part of a static DTB that got passed in once you insert it in. And there's a config.fs interface that's used to specify it. So you basically have the fragment blob, and you make a directory, and then you copy the blob in, and it uses that to load the blob in using the kernel firmware loader. And that's basically the user interface to it. It's very simple. So let's look at DT fragment formats. So Pentel Sentenu did all this work. He's got a DT, an overlay-enabled DTC on his GitHub page, and so you need to use that to get this syntax. The way it works is there's the plugin identifier, and that notifies DTC that it's processing a fragment instead of a full device tree source. The compiler, in this case, so this BAS node, so we're getting into how this compiler works. Just like any compiler or assembler, you would go and it takes a pass through, and it's going to assign incrementally. In this case, it assigns a 1 into this node, right? So this node has to have some identifier, right? So it assigns that, okay? And then for this guy, this QUX, and this is an example he had, real simple to show the basics. If you're referencing this node, this is a P handle referencing a local node, it can resolve it. So it does. It will assign 1 in there. It was locally resolved. But it knows it's in fragment compiling mode because we told it plug in. It gets down to here, and it sees QUX, and it's referring to something called ANFU, a very popular name. And so it will actually put it in a table for fix-ups. So there's a symbol table. Anything that it can't resolve in the file locally, it will go put in a table. So what that looks like is if I compiled that, and there's a tool to dump DTBs back out. So I compile it, and then you dump it back out. You can see that the QUX node, it couldn't be resolved, so it's put in that fix-up section. Okay, so that's so you can see how this works. Something that can't resolve, you have that in the DTBO, and then the kernel can go through that list and resolve against the live tree anything that's in that fix-ups area. And you can see that the local fix-ups are noted as well, right? So QUX was actually resolved within that fragment. All right, so now I want to show you how to add an I2C device the easy way. So if you've got a platform where you can run 319 and you want to interface the I2C device exactly, which you can do this on BeagleBone, again, plugging BeagleBone. I don't get any royalties. So what I would do, this is the actual full fragment, okay, to do the previous example. This time, what's nice is I don't have to show you out of context or anything. This is the whole thing. So DTS V1, plug in, and so it's got this interesting format, and it's a little daunting at first, but you can kind of see the same patterns. So we went over these nodes, right? This I2C pins is straight out of that information earlier, okay? And the same thing with the child node and all of the I2C1 information, okay, is in there. And all that's happening is you can have any number of fragments, and what you do is you identify them as fragment, and you do need unique unit addresses, okay? And they don't have to start zero-based, but it's just convention. And then what you say is, I've got an overlay I want to apply. The target is the AM335X, and I must have gone in and typoed in that, editing this, PinMux node. If you saw in my fragment, that's actually where you're adding this piece. So you say, that's the node that I want to overlay something into, all right? And then after the target, you say overlay, and you start a new child node, and you put that information. I want to put this PinMux I2C1 pins node inside there, okay? Terminate everything properly with brackets, and the same thing again, fragment at 1, the target is the I2C1 node, and I want to overlay all of this information into the I2C1 node in the base tree, all right? So I just put that in an AT24 I2C1 DTS file. It's just my fragment. And then I can build it. We build it the same way there. And to actually get this activated, I just make dir on /config device tree overlays, and then an AT24 I2C1. It doesn't really matter what the name of that is. Could be test. That actually prepares the directory. Within this directory, once you make it, a DTBO file will appear, and all you do is you copy the DTBO that we compiled from that fragment, you copy that into that file that was created, and when you do that, it modifies the live tree, it enables the I2C1 controller, it adds the AT24 device at address 50, and both devices get instantiated. And if you have the AT24 driver built as a module on your system, it would immediately mod probe that in as well, right, just from doing all this. So it's essentially you're hot plugging in that stuff and notifying the kernel.
Does that overlay functionality have to be enabled explicitly in the kernel?
Yes. Yeah, config OF dynamic. It's that original symbol, the original config option, but it's actually fixed now. It didn't work this way previously. So 319 is when this last piece went in. All of the actual overlay piece. There was a bunch of work in 317 that was done to fix the live tree, all the transactions, and so that you could unwind them, because when you remove them, there was a lot of tracking that wasn't done on adding them, so it was all destructive. So they fixed all the infrastructure in like 317. There was a couple Windows lag before the overlay stuff got merged. And then likewise, you can remove these devices by, all you have to do is rmdir. So if you haven't worked with config.fs before, it's got different semantics from sysfs type things where you're mostly gathering information and touching nodes that sysfs, just in case nobody knows the difference between those, is it's all things that are created by the kernel. Config.fs are things that are all user-driven. So that's why you see this. You actually are creating a kernel object when you make this directory, and then it exposes that interface. And
You want your driver to be a module in this case? You use a dynamic device. It's not going to be built in, right?
it doesn't have to. I was trying to keep this to where we could talk a lot about this, but that was the last piece of it. So that's good. We're into this part. You don't need to use a module driver. That was an example to show how clean it is end to end. I mean, you could just as easily instantiate that thing and then use I2C detect and I2C get and I2C dev user space interfaces to go write whatever you want in user space to it. But you have to turn the controller on to do any of that. You don't need to instantiate the AT24 at a certain address to use I2C dev in user space.
Or built in, it could still be done, the module could still, the driver could still get a bind and unbind, right?
Yeah. So like this, you could unbind the AT24 driver, and then you could go whack it directly from user space with the I2C dev interface.
More questions? Let me know so I can get you the mic.
Yeah.
So you said device tree does actually get used on x86. I know you have things like I2S controllers on that. How does that traditionally done? Through ACI or something?
I'm being a little snarky about that. It was one platform, right? It's like a set-top box platform. It was quite a bit different. The Falcon files, I went and looked at it like a year ago when I first realized it was there, and it's been kind of a running joke that there's something there. They actually have exactly that. They've got I2S and I2C stuff and a whole bunch defined in there. They didn't have a traditional BIOS or UEFI on there with ACPI, the SDST and DST-DT files that would describe all those kind of things in a typical, more PC-like system, right? So yeah, it's an anomaly basically. But I will say there are embedded industrial x86 customers with carrier board type designs that are actually going this route. They're using DT on their systems because they're, again, quite a bit different, and they need the ability to dynamically change the hardware. I don't know. It's just as difficult to write those things, right?
Yeah, I was just kind of curious from the perspective of something like the Minoboard Max, where it is a kind of halfway between a PC architecture and one of those embedded platforms.
Yeah, so they actually they have ACPI 5.0 coming. I was just talking to John Hawley because it's actually kind of a chore on there. You have to use like a little custom module to instantiate stuff, right? Or use some of the sysfs interface. Well, you can't do everything, right? You know, to hook up like GPIO and I2C resources, you have to use a module on that platform to get that to happen. And they have ACPI 5.0 support coming, which allows them to instantiate devices in DST-DTs, which is analogous to this type of thing. I don't know how well that works at runtime. I don't work on those kind of platforms. Yes?
So you showed an example where you had a DTO overlay that was dynamically loaded, and your I2C section was shown as an overlay. But if it didn't exist in the original DTS, would you still say overlay there?
Yeah, you can actually overlay a whole controller node. Yeah, the overlay is a keyword in this case. Okay.
Right. So if that I2C one didn't exist in the original DTS, would you still use that syntax?
Yeah, you would pick the parent node. exactly what Stephanie's saying. So there would be another node that you would target that's above that, right?
Way back in the old days, we used to have DTS files that had placeholders, essentially, that OpenBoot would fill in. Does that still work? That is, rather than me having to do this from the kernel and file system, can I still have essentially placeholder entry points in my DTS file?
You're still going to have to compile it, right? And it's all got to resolve.
Right, but U-Boot used to be able to patch those.
Yeah. It has limited ability to edit the
blob.
FTT. Yeah, exactly. Yeah, it's extremely limited. This resolver is a lot more powerful. I will tell you that I found out 2 days ago that the way that Raspberry Pi does it, they actually have overlay support. And what they mean, they don't mean this. They mean they have, they use the same device tree compiler with the same, they actually use the same format to generate them, but their bootloader on the video core, the GPU, you know how it starts the ARM processor on the Raspberry Pi, right? It will actually process a set of fragments, and it will resolve in that firmware. And then it passes a glued, an NDTB to the kernel. So their kernel doesn't have any of this support because it's a bit older, but they actually use the same fragment DTBOs, but they're actually wrote their own resolver.
Yeah, because the flexibility was you could have the firmware on the board know about like the pin settings, the read on boot,
right.
Resistor settings and things. And okay, we do have these two UARTs, but wait a minute, we're using this PCI bus and that SATA port kind of thing.
Right.
And then the kernel didn't have to have quite so many copies of DTSs.
Right.
Because you could fill it in at runtime.
Yeah. The big thing that drove this was there's some deployment use cases with FPGAs, right, where you're
I remember all those.
You're reconfiguring. I mean, that was the big driver.
Yeah.
All the Xilinx and Altera folks need this. There's also there's a number of cases where you need very fast boot, like automotive, where you can't be doing a lot of handling of the DTB in the bootloader. You can't touch it at all, and you have to have the base one that gets you booted up and gets the basic stuff done, but then they might add some other features in with overlays.
This overlay thing is really the way of migrating that away from having the bootloader fix it up.
Yeah, it's a different way of doing it. It's more flexible. It addresses more use cases. And in fact, what the Raspberry Pi folks are doing, they could easily move to the kernel resolver instead of their early one. There's also some work I don't cover where there's some use cases for quirks. Instead of having separate files for the BeagleBone white and black, for example, you can actually use overlays and have a common file, and based on it reading the EEPROM very early, it will pick which nodes it actually uses out of a common file. But that's being discussed very earnestly right now on the list. So good. I come back to that. Go ahead, Jason.
One of the practical issues we've had in using overlays is that a lot of the device drivers were never meant to be unbound. A lot of the device drivers were written as platform devices, and the unbound functions essentially have never been tested.
Right.
And then you issue and you get oopses that are reasonably isolated. I don't know if the isolation is any better with the new mechanisms, but you can't really get back to make other configurations because it just locks out. What do you see as the future for getting all these drivers to unbind, and have people going and addressing those issues? Is there any sort of exhaustive
testing? We found somebody to pay for it all. It's Google. And I tell you, I'm not kidding. On Project Ara, they have almost the same use cases because they're tunneling all of these legacy things over their Unipro architecture, and it's all hot pluggable modules. So they're already resolving the fact that GPIO doesn't hot unplug. So if you want to take a GPIO controller out, yeah, that's actually getting addressed on Google's dime right now. Yeah. So there's some work going in on that and also on the I2C side. So the good news is, unlike 2 years ago where it was like the BeagleBone, camp was, screaming for this and showing this use case, everybody's got it. Everybody's kind of caught up. There's Project Ara with a lot of funding behind it. There's multiple platforms. It's not just the community boards. There's a lot of people with high-end networking systems with carrier boards and so forth. I know we discussed that one last night, right? Yep. That are driving these. So it's getting better.
So we'll just say you're welcome for that one.
Yeah.
But the other issue that we see coming up is the resource management. So there's still a lot of a weakness in resource management for multiple processors. So in the case of the BeagleBone, there still gives a cases. There's the microcontrollers that can access things like the GPIOs and other peripherals, and a lot of people struggle to get the interfaces defined properly for using the microcontrollers and selecting those dynamically, switching back and forth. Is there a future for proper resource management for the various registers for other CPUs in the system that aren't just the symmetric stuff, right? So
yeah, and it's not a unique problem to the smaller end processors. I know that people struggled with how do you deal with, this is several years back, how do you deal with describing an 8-core system that's really running in AMP mode, not an SMP, which was a lot of the high-end PowerPC, MIPS networking stuff, right? Do you have, if you've got 4 cores running SMP and 4 running AMP, is there 5 DTBs going in the system? Because those are all independent systems. They're running another copy of an OS, right, in AMP. And it's almost the same situation. The problem with DT was, and it's just like the dynamic thing, right? It took a long time to change that model because it was always designed static, right? Here's the static hardware. Hardware is static, and it's not true. And it took 3 years from time Cape Bus until this went in the kernel to convince the world that hardware is no longer static, right? I mean, and FPGAs basically became the canonical case, to carry that. I think we still have that issue with the fact that DTS or device tree in general was from the perspective of a single system owning all the resources, or a single processor owning all the resources in the system. And how do you deal with that M3 or your PRU that owns resources? I don't see any movement there, to answer your question. I mean, it's definitely a problem. It's come up a few times, but I think everybody's avoiding it, as usual.
All right, sweet. So let's have a big thank you for Matt.
Thank you for coming.
So feel free to ask a couple questions as he, I guess, walks out of here and backs up, right? So you're going to be here for the whole weekend, right?
I'm going to be here till tomorrow.
All right, so yeah. Definitely it's like Sunday. We've got a really good set of stuff coming. So, remember, this is your event. So you see something that needs a little help, go for it. Thanks.